Hello and welcome to our webinar. My name is Anna Paksad. I am the Imaging Application Scientist here at Gatan and will be hosting the webinar today with Dr. Roberto dos Reis from Northwestern University. Next slide, please. Roberto is specialized in advanced characterization of vast range of materials using transmission electron microscopy techniques. He has Bachelor of Science, Master of Science, and Ph.D. degrees in physics from Federal University of Rio Grande do Sul in Brazil, where he worked on synthesis and characterization of semiconductor thin films. During his Ph.D. studies, he was a long-term visiting scholar at Lawrence Berkeley National Lab in California, working under supervision of Dr. Susanna Weber on characterization of highly mismatched 3,5 and 2,5 semiconductor alloys for photovoltaic applications. From 2014 to 2018, Roberto worked alongside Dr. Yuli Dahlman and Dr. Jim Sisson as a postdoctoral researcher at the National Center for Electron Microscopy facility of the Molecular Foundry, applying advanced electron diffraction techniques, including 4D STEM, to a variety of materials, as well as collaborating with several users in a multidisciplinary environment. In September of 2018, he joined Northwestern University as Research Assistant Professor in the Department of Material Science and Engineering, and he also acts as the Scientific Officer for Professor Vinayak Dravid at Nuance. His research is focused on developing and applying experimental TEM-based methods to convey a direct relationship between the properties and the atomic structure. Just a reminder, during the webinar, you can submit your questions via the question pane. We will try to answer your questions after Roberto's presentation is done, and if any question remains unanswered due to lack of time, we will respond in the next few days via email. Okay, with that, I would like to give the microphone to Roberto to tell us more about the applications of direct detectors in material science. Roberto?
Hello everyone, and thank you for that introduction, Anna. So my name is Roberto dos Reis, and I'm very excited today to talk about this the new applications for direct detectors. And here's the webinar outline. I'm going to talk a little bit about where I am now in the facility here at Northwestern University. And I give a little bit of overview of direct detectors and how they impact not only the cryo-EM, the cryo for more biological work, but also in the material science realm. After that, I'm going to give you a few examples of works that have people here at Northwestern are doing, and finalize with some remarks in the summary. So to start off, I'm part of I work for Nuance Center and here in Northwestern. So Shine is Nuance is part of Shine. And Shine is an open access initiative that operates under Northwestern International Institute for Nanotechnology, IIN, and works in partnership with the Chicago and the Institute for Molecular Engineering at Chicago. So the Shine facility is an open access user facility, so that brings together very broad experience in a very nice suite of capabilities, not only in hard materials, but more like traditional soft materials, such as biological polymers, fluidic systems, but also new systems that combine soft and hard materials and interfaces. So like I mentioned once, is a unit of Shine It is a regional center of excellence here under the National Nanotechnology Coordinated Infrastructure. So a big portion of our work here is on education and outreach programs, as we are attached to a university on campus. So we work on several programs, like bringing undergrads to expose them to research, and also programs such as nanojournalism that brings students from Northwestern School of Journalism to tell stories about science, and also teach scientists how to tell better stories. And then you're all welcome to visit our website and learn more. So most of the results and examples that I'm going to show here are taken with just 2 microscopes. So within Nuance, we have an electron probe instrumentation center. So there we currently have 5 SEMs, 2 FIBs, and 7 TMs. So, and they are all managed by our very excellent staff here, Dr. Xiaobing Hu, Tirza Abbott, and Paul Smith. And you're welcome also to check our website and see more of it. So with that, I'm going to start talking about the overview of electron direct detectors, right? So many of the demanding requirements for this for the detector performance actually were imposed by the applications in electron cryo microscopy, right? So you probably have seen a lot of buzz in the community, and then even the Nobel Prize a couple of years ago was awarded to the pioneers in cryo-EM. And most of this improvement in the last few years came for the fact that from the improvement of the direct detectors here. So, and much of the detector technology also is based on the development of microelectronics itself, right? And then that have allowed the design of these detectors with a much finer pixel size, faster readout, and also sufficiently radiation hard for practical use, especially in electron microscopes, right? So I'm going to run a quick video here, actually courtesy of Gatan. So this explains pretty well how they work. So during counting mode, so the direct detector cameras identify individual events, electron events, right? And they reach the sensor. To do this efficiently, the sensor frame rate must run fast enough to identify individual events separately, right? For example, here in this part of the movie, you see at a frame rate of 40 frames per second, you're not able to identify these events separately, right? And this and the fact that you can do that much faster today allow us to open up different many new avenues for imaging, especially in sensitive materials such as biological and soft. So as I'm showing here a chart from the cryo-EM community, actually showing the resolution as a function of the molecule size and molecular weight here. So as of today, and actually was having recently published a new record for a low molecular weight. This one pointed out here by this red arrow. So it can get the resolution up to about 3 angstroms for a pretty low molecule size. So, and then you can get that with there are many different vendors around here, and this is a nice comparison brought by Gatan here. So it really coming from a more a hard materials from the hard materials perspective, how can you benefit from that, right? So how can you use that direct detectors to open different types of experiments, and then start exploring different sort of materials too. So here a couple of examples that how the direct detectors are facilitating, and I say quote unquote new techniques, which are not new, but now you can get much better view of this processes here. So this is an example of in-situ TM that was done here at Northwestern. This is a project from postdoc here, Kuhn here. So she was looking here at the early stage formation of copper nanosheets. So this nanosheets after are used for catalysis, for example. So you can really see the process happening, and one benefit of the direct detectors is the fact that you are counting electrons, right? So you know exactly how much dose you are applying to your sample. And for samples, for materials like this, where the dose is pretty critical and then actually triggers the process, it's very fundamental to know the how dose dose you are applying to that. So if I play this video again, you're gonna see that happening. So yeah. So another example here, I'm gonna go back one slide. It's from the literature. This is a work from UC Berkeley, also using direct electron detectors. You can go further up in the magnification and see those crystals growing as you image. And this is pretty unique, right? And that was not possible a couple of years ago without direct detectors. So another type of modality that some of you might be aware of is scanning diffraction, or so-called 4D STEM. So in standard, I have a Reis schematic here for a STEM, a scanning transmission electron microscope, where you have like a probe form, and you have your cross path here, and then you have at the end of your diffraction plane, you have a electron beam, right? So just a beam over there. So if you add in a traditional STEM mode, what you usually do is just you collect this data in the monolithic detector, such as annular dark field, ADF here for short, or high angle annular dark field, HADF, or annular bright field or bright field detectors, right? So and at the same time that you collect that, and then the improvement of the microscope itself with the aberration correctors and so on brought us to a very brought us fantastic work in using high resolution STEM, where you can have resolution down to, you can see down to 0.5 angstroms pretty much. So, but when you put a sample in, so you see in the far field, you have your what we call conversion beam electron diffraction pattern, or CBAT here for short. And with improvement of the direct detectors, what you can do now is as you raster the beam in scanning mode, you can collect for each of the pixels in your stem, you can collect a diffraction pattern. And that also brought us a lot of early work in CBAT. Being a fan of CBAT myself, you can really benefit of the information that comes from there. So you pretty much have all you need from a sample. Being able to collect that, and being able to collect that at each proposition is very critical here. So for more information about that, I give you a reference here. There was a very, very nice review on 4D SEM and related techniques by calling authors here. So if you want to learn more about that, you can. This is a good start. It gives a very good overview of everything that is going on in this field. So continue on. I'm going to start showing some of the examples here from Northwestern using the new K3 IS, so that we had here installed in one of our microscopes. So the first example that I want to show is a pretty unique way to visualize the structural dynamics in the transition metal dichalcogenides using external electric fields, meaning you bias the sample and visualize in situ what's going on in your structure. So the motivation here, and this is work from one of our students here, actually, Murthy. So the motivation here is that the point and line defects, in those 2D materials, they serve as an effective path for tuning all the electronics and the catalytic properties in the future. And also, all the electronic structures can be modulated by tuning the grain boundary tilt angle. So you might, if you're not aware of, there are many works now in twisted graphene, for example, on having stacking 2 layers of graphenes, and that triggers a lot of different properties. And also for not for unconventional 2-dimensional materials such as moly disulfide and its variations. So for transition metal, for TMDs here, so the grain boundaries, and have been shown that grain boundaries serve as sites for preferential heating and also oxidation during a real device operation. So to study all these properties, and this is one thing that I want to point out here, is that all these motivations here could not be resolved, and this is still not resolved until we had access to direct imaging of these materials with external biasing. So to reach to that point, we had to go through a very unique fabrication process here. So this is I'm showing you in the schematic here for the device fabrication. So we have the metal electrodes. They're first picked up from the substrate, right? And then using a polymer film, and then they are placed on a TM grid for further manufacture. So they have a monolayer of moly disulfide film here, and then you pattern those electrodes on top of them. So you have electrodes bottom and top. So that means you have a real device, and you are mimicking a potential real device in the future. So you want to really see what happened when you bias. We want to be as close as possible to a real life case here. Then at the end, what you have is, this is an SEM image here at the bottom left. So you have the contacts, right? So if you look at the right, bottom right, you have the contacts, the film on top of it, and then in between those contacts, that's the region of interest that we want to image, right? So moving on. So the first thing we do is check the quality of the sample. And this is one of the first images taken with using the K3 IS from Gatan, actually. So this is a very large field of view of the TMD. So we have like grain boundaries going on here, have different tilt angles and so on. But the goal here was to look at the overall quality of the sample, right? And then you can even, if I play this short move here, and this is how the image was collected, right? So you can fractionate the total dose and make sure that you're not damaging your samples too. And then with that feature, you can also use those frames to align and obtain the final image like you see here in the left. So the first thing that you want to see here is the stability of the sample under the electron beam, right? So when no external bias is applied. And I'm going to play this short move here to see. So this is one of open areas that happened during the process of external biasing. So after that, we image to look at how stable is this kind of structure under the same experimental conditions that we take the images. So you can see here, and then it's pretty stable up to a minute or so, right? So then the sample flies out of the field of view. So this is, and then again, I want to point out here that this is a very unique feature from the direct detectors. You can make sure that your samples are not degrading during the process of imaging, right? And this is very important for many cases. So moving on to the next one. So one region that we are interested here is that this type of channels that are open during the external biasing. So this is, we're gonna look at this image, look at this video here, and then I'm going to talk over it. But just to give an idea, this is the IV curve that was applied during this process. So you can see that at one point, if you look at this little bridges that are like holding together those two pieces of material, right? At some point, when you get to a certain voltage, they completely rupture. And then you can see some snapshots here on B and C, right? So this narrow, like little ribbon here completely falls off after like 1 volt of external biasing here. And then, so being able to image this at high resolution also enable us to start looking at different features of the material, right? So this is just a quick example of things that you potentially can do depending on your sample, of course. But this is just a measurement of a localized strain field at the edges of this moly disulfide. So you can imagine here that by collecting that for a minute or 2 minutes or so with the high quality image, you can see the evolution of the strain in certain regions of your sample, right? So this is just to give you an idea that the potential that you have for this type of experiments, right? And this is in combination of it's a combination of in situ and like direct imaging. So you can think about applying heating, applying external some photosensitive materials, for example. You can apply and see degradation. There are a lot of improvements now in like in situ holders, like liquid cells, the gas cells, and so on. This is a very good combination of different things that you can do in the microscope these days. So keeping in the same realm here, one thing that we are trying, we started to do here is looking at the interfacial charge accumulation, also in the same type of geometry, but now adding a layer on top of the moly, actually at the bottom of moly disulfide here. So I'm just going to give you a quick example what is possible to do. So, and this is like a render image of the stack that we have. We have a HBN, so it's a boron nitride at the bottom, and the moly disulfide on top. And this is more like your real device that you might see in the future being available commercially, hopefully. And then we went through, actually Akshay here also did the same process of manufacturing these little devices, and then tested to confirm that you have a pretty good contact. And we check with the standard select area diffraction here. You can see there's a little offset between moly disulfide and boron nitride, and this is something very important that you can actually change that depending on the type of feature that you want to have from type of property you want to have from your sample. So what we're trying to do here is a little bit more advanced technique called a differential phase contrast, where we use the geometry that I introduced through the 4D STEM geometry experiments in the microscope. So what you do is just raster your beam through an area of your sample. In this case here, we raster it through an interface between moly disulfide and HBN. And then what you expect to see here is when you apply external electric field, you have an accumulation of charge at the interface. And that charge shifts your beam locally, your center being in your stem, in your diffraction pattern, actually. And then that is directly related to the charge accumulation in these materials, and then some other materials too. And then you might have seen other papers very nicely showing like a high resolution DPC signal. And then one thing unique about this, and this is this project here, is the fact that you're combining an extra in-situ component, right? So, and then also you incorporate sample vibration and other issues that you not allow you to do to run that at very high resolution here. So if you look at on the bottom right here, this is the actual DPC signal, and then you see this is the interface around here 300, and this is like a number of pixels. So at from 100 to 500 roughly, you have that charge accumulation, and that changes depending of the external voltage that you're applying to your sample. So changing a little bit of material systems here. So one type of material that people really started to look at with the new direct detectors are the so-called metal organic frameworks, so MOFs for short here. And then, well, one thing that people and researchers around are very interested is to look at the structure at high resolution, right? So, and this sort of thing was completely impossible before the direct detectors. So one example I want to show here is from the collaboration with Professor Omar Farha here at Northwestern. And then what they do, they synthesize a variety of MOF structure here. And then one thing that is particularly interesting here is the NU 1000. NU is short for Northwestern University here. So it was synthesized here for Professor Omar Farah's group. And then one thing they're interested here is to include those like PW12. They are like catalytic particles, right? And they want to embed them in MOFs. And one thing they are very interested is to look at the position of these dopants in the MOF structure, right? It's a long way to get there in terms of images, and then it's a very complicated type of experiment today, and then it's much easier now with the direct detectors, but it's still it's a combination of knowledge of electron microscope, TM in general, and also synthesis and sample preparation, especially here. And we have borrowed a lot of techniques from the biocrio community to prepare these samples here, and to make them available for imaging under the electron microscope. So here on the left, I show the structure here, and then they tune that the gap, right, the pores of the MOF according to the application. So for this case here, they predicted a pore around 30 angstroms, and the small pore here about 12 angstroms. And then, like I mentioned before, they're looking at the positions of the PW12 here, or they also call POM here for short. And if you look at the SEM on the right here, so they are pretty they're relatively large particles, so you have to go through a sample preparation process here. And then one thing that I want to point out here is this PW12 are sensitive to the environment, and that's why they want to disperse this in like solid support, such as MOFs here. So the first thing that we do for this type of samples, and then we are exploring like different synthesis too, is how sensitive they are to the electron beam, right? So, and this is a portion of the image collected with the K3 IS here, and I'm going to show like different frames with different with accumulated dose here, right? So this is the first frame, something around 0.2 electrons per angstrom square here, and then as you increase the dose, we start revealing this structure, right? So then you have something that's your threshold for this sample is about like 20 to 30 electrons per angstrom square total. And it really depends on your sample as well. So if you there are other groups, I can refer some works from KAUST in Saudi Arabia. They have done like pretty good work on imaging MOFs, and it really depends on the type of MOF that you're working with. You can apply more or less electrons to image, and depends on the resolution that you want to achieve, and also the purpose of your imaging, right? So for this one here, I'm going to show you a quick example. This is collected with the K3 IS, 55 frames. The total dose here was around 20 electrons per angstrom square. And I want to focus on this little section here, and then bring it up on the right image here. You can see after processing, image processing here, which we also borrow from the cryo community. you can review size of pores, and also you can look at this at the regions that are like a little brighter. Those are the indicated position of the MOFs, the PW12 here in this structure. So another very exciting project here. This is a very different type of material that before working with this, I haven't seen that before, and really requires also a combination of electron microscopy knowledge and knowledge of sample preparation. In this case, also like a very low dose FIB preparation, sample preparation, and combination with techniques from cryo-EM as well. And this is a project that is Paul Smith here from Northwestern. He's also one of the facility managers here at Nuance. So he did a pretty nice job on looking at this the enamel, which is like part of your tooth here. So this is actually the outer enamel is this region here close to the surface of your tooth. So if you look at this panel here, you can image these materials at different scales, right? So even at a very high resolution, and this is the work from Paul that he has done in collaboration with Cornell folks, and then they use cryo-STEM here to achieve, to be able to image them at high resolution. But one thing that we are interested here in using this unique capability of direct detectors is look at the a larger region and check how the grains are oriented to each other, right? And this is has some other consequences, like for example, appearance of cavities or how your tooth breaks and so on. And then it's very important to look at this grains and then correlate them with actually like a real life problem, right? So one thing that we did here, it was using also 4D STEM here for to look at the diffraction patterns and use them to map out the grains. Right, so just a quick note here on the experimental conditions for this specific project. So we knew that the dose threshold for this material, which is lands in the middle of like hard and soft materials, right? So it's about 10 to 3 electrons per angstrom square, which is not very low, but it's lower than the standard STEM images that you take on a daily basis. And here we look at the one, and then you can actually control that dose using the fact that the cameras today, you can count how many electrons are landing at the surface of the detector. So you can use the vacuum probe, so-called vacuum probe, right, to actually know exactly how much electrons are you putting in a sample here. So, and this is just an example of a single diffraction here, and this is the average over more than 65,000 diffractions here. So if you look at the panel on the right, so this is a couple regions that we want to take a close look here. And this is a technique so-called virtual detectors, right? In your like standard bright field, dark field images in your standard TM, so you have to tilt your sample, go to tubing conditions, and repeat that many times, right, to get a complete map of your grains. So with the collection of this large data set of diffractions, you can actually reproduce that bright field and dark field in any fashion here. So you can see, for example, here, so if you can reproduce your bright field stem image by averaging, integrating the intensity in the central beam. So you can see here on the right, this would be your bright field image if you just collect that with your monolithic detector, right? Another example here, so if you look at this 2 grains, this diffraction here, sorry, in yellow, so you highlight some of them, and then you can start building that map of a bright field, dark field and bright field image, and then highlight regions that you're actually interested in look at. And then another example here on the bottom right is the one that is opposite. So you can see here, so you have 2 very distinct, like sort of big grains here that's highlighted in green, and then the one on the left, on the far right, that is actually reflects. Its reflection is part of both yellow and green here. And then you can also, you get that for free, a little bit of lattice here as well, which can be used in the future for applying other processing methods, which I'm gonna talk a little bit more about in a few minutes. So, and then you can look at different orientations as well. So here is another orientation of the same part of a sample. So you have those like very like ribbon-like features, and then you can use the same type of experiment to start use the same set of diffractions to measure a strain, right? So this is a work in progress here, and then we're gonna hear more from this pretty soon. So moving up a little bit to a little bit more, say, exotic experiments, which like phase contrast stem imaging applied to soft materials. So this is, I want to leave this more like an idea for future. We have been using this technique here. I'm going to show like one example. But first I want to start with and the phase contrast stem image that I'm going to talk about here is specifically ptychography. So why we want to use phase contrast stem in soft materials, right? So I give you an example here of me trying to imaging a moth just to show that I damaged the sample pretty much. So look at on the left, right. This is your typical ADF image in your stem, and on the right you have an ABF. So after one quick pass using your standard conditions in the microscope, you completely your sample is completely useless. So some areas, and this is a good comparison here, some areas retain the crystallinity, and then of course this area here was not heated by the electrons yet. So you have a very, very short time to collect stem images from these materials. And so to be able to image them and to do stem, you do need those efficient methods here. And then there are other imaging methods, stem phase images here. I want to talk specifically about ptychography. And then specifically within ptychography and electroptychography, of course, 2 modes, right? One is a focus probe, where your sample is placed exactly where your probe is focused. So this is the, I'm just going to take a step back here and just introduce a little bit of ptychography for those that are not aware of. It is pretty much a computational imaging technique. So, and then we use the fact that detectors can record an extensive data set, right, consisting of many of interference patterns. So say if you remember a couple of slides ago, I show some of the seabed patterns, right? So you can see the overlap disks, and then that shows the interference between the adjacent patterns here. And then of course, then a computer, we applied a computer algorithm of some type. There are many types around today, depending on the experimental configuration as well. It has like pretty much three advantages. It does not depend of a good quality lens. So we ideally we would use like a free lens setup, like folks in the X-ray community do, and then use or you don't have to use any lens at all, actually, except for the one that form your probe. And then also it can record image wave in phase as well as intensity. So this is very important too in the future. So this is the first one that I want to point out. And then most of the electron ptychography work that you see around in high resolution today is taken using this configuration here, right? So this is the image that you see in your far field. It's a diffraction pattern. The conversion being electron diffraction pattern here. And then the other mode that I want to talk about, and this is going to be important for, especially for beam sensitive materials here, is that when you defocus the probe here, you have some sort of your, for the aficionados over there, so the Fresnel images here, and then some your dark field images outside, right? So you obtain that by moving your sample to a different point of your probe formation here, so outside of the focal point of the crossover, sorry, or defocusing the beam. So, and then this is very used on X-ray as well. So just a quick example, this is a work that I've done in the past with folks at NSAM in Berkeley. So this was using a direct electron detector, but was recorded with so-called linear mode. So it was not like directly counting the electrons. It was just today with the K3 IS, you can actually count that. And collect the scattering diffraction. So this is mimicking this new capability that we have now. So just to have an idea how and this was lowering the dose by a significant amount up down to 10 to 3 electrons per angstrom square here. And then with that type of configuration, and this is like a focus probe mode here, ptychography, you can obtain like some very neat high resolution of this halide perovskites, where you can see not only the high Z element here, which you can see in a ADF image, but also your halide here, in this case chloride or bromide here. But we found out there are some limitations, and then now we are in the progress of overcome that with the new technologies, which was like when you try to image those materials that are more sensitive, such as hybrid materials, metal organic, metal halides, sorry, you using the same configuration here, you pretty much damage the sample. Although you get some of the information about the cage lattice, but not really. It's still far from the nice image that you get up here, right? So that's some of the limitations that we had before. So now what we are working on, and this is an example of the defocus, right? And this is actually the using like very unique configuration where you use the transmission beam in SEM. And then you collect that diffraction patterns and reconstruct these images. And then for more information, just go to this reference. It's very nice paper, and then really fundamental on this defocus probe ptychography. And then just for comparison here now, if you look at the like standard cameras such as 1VO or Reis if you're a Gatan customer, or some other detectors from different companies, you can see if you lower the dose by a significant amount, you pretty much don't see your beam, and then your image is full of noise, and then you have to go through a very hard like processing after that. With the K3 IS, for example, this is the same, exactly applying the same dose, the same conditions here. You have a much easy to see your central beam here, right? So you can definitely get information out of this diffraction, conversion beam diffraction pattern here. And I want to show you a quick example here of imaging one probe on the defocus mode, imaging one of those moths that I showed earlier. So you see the structure within your central beam, and then you can start using that to applying ptychographic methods to retrieve the structure here. So I guess I'm going to leave you with that, and we're running a little bit short on time. But I want to give you like an overview of what we talked today. So definitely, like direct detectors transform the electron microscopy community. So not only the cryo-EM community, but also now the materials, the hard materials, and soft materials that lends within very sensitive to within very sensitive materials and hard materials. Definitely, new materials can be imaged. They're not imaged before. So I give you a quick example here on the top right. This is a work here also from Northwestern, where you can map those like polymer films and draw an orientation mapping with a high resolution TEM here at the low dose. Other examples here in the hard material. This is the nickel tungsten alloy from Xiaobing here. You can use that to produce a strain map, to make a strain maps, for example, and also open like new possibilities for new experimental designs in microscopy. For example, here this is one thing that we are developing here. It's called ptychography with the control rotation tomography. So you can you collect those ptychographic diffraction patterns and use that to reconstruct your 3D structure here. Let's see if I can play this to show you. I don't know if you're not playing. And also one important factor here is that, and then the community got much better on this in the last years, is that it pushed the data analysis and data engineering of these large data sets that are coming from these detectors, right? So this is still it's still in the early stage, I would say, but it's much more it's much better than it was a few years ago. So there are codes around, they're freely available, and groups working on this, including Northwestern. And then you can definitely, and then you're going to see much more of this in the future, and you're going to see the community benefiting of this evolution, I would say. So with that, I would like to thank you. I don't do any synthesis here, so I pretty much take data and analyze. So I cannot thank enough all the collaborations, all the collaborators here. and then also Gatan folks for inviting me to give the seminar. And I guess you have quick minutes for questions, or maybe you're running short. I know.
Thank you so much, Roberto. Yes, we're almost out of time. I would like to remind everyone that you can still submit your questions, and we will answer all of the questions via email within the next few days. Maybe if you can just quickly answer one question, because we talked about low dose
Yes.
a lot. Can you say what is the minimum dose that can be used on the K3 IS camera that will still give you meaningful information in the images?
Yeah, that's a good question. So we have tried on different materials, and that really depends on the material that you're working, right? And then how thin it is, how much they scatter, and what's the elements you're trying to image. But I would say in the standard full frame, which is about 5K by 4K, you can get some very decent images from moths with say 1 electrons per length square, 1 to 2, I would say.
Okay. All right. I think we'll wrap it up here, and I'd like to thank you, Roberto, again for accepting our invitation and a great talk, and everyone for attending our webinar. Have a wonderful rest of your days.